Swayam Prabha, Digital India, Educated India.
Good afternoon, everyone. In this particular course, we are going to study the introduction to operations research as a part of operations research 1, and this is our first lecture. So introduction to operations research, as the name suggests, the operations research, what exactly it does. Operations research uses analytical methods for decision making, and it's about better use of resources. So there are various things out here. The first are, what are these analytical methods? These analytical methods could be linear programming, transportation algorithms, assignment algorithms, branch and bound techniques, nonlinear programming, simulation, queuing theory, stochastic processes, and so on. Now, all these different analytical methods, how are they used for decision making? You see, most of the management situations, they are using resources. Now, when we are using resources, resources are not available in infinite quantity. There are finite limits to the resources. And since the resources are finite, what usually happens that one or the other resource actually may become a bottleneck resource. So when bottleneck resources are present, we might be interested in producing certain quantities in certain numbers, but we may not be successful. What really happens that when we are trying to produce so much of certain products, we are not able to do it because some resource is bottleneck. Even if you remove the bottleneck of that particular resource, it does not mean that you are in a position to really make as many as you wish. What can actually happen is that some other resource then can become a bottleneck resource. Having said that, the operations research could be used in so many different kinds of problems, and here are some examples. The first one, the resource allocation problems. You see, the resource allocation problems essentially, just now I gave some idea about how there are different resources which are required, let's say, to produce something, and invariably some or the other resource becomes a bottleneck resource. Thereafter, we have the transportation and transshipment problems. Whenever you are trying to move something from one place to the other, there will be always the material has to be stored, maybe some sort of stores, and from one store to the other, the demand points when you are sending the material, there will be requirement of certain vehicles or other kind of thing which actually require costs. So how to minimize these costs, that is the essential part of the transportation and transshipment problems. Assignment problem, on the other hand, are when we are assigning, let's say, some bids to the bidders, maybe some jobs to some machines, how exactly we do it in the best possible manner. Then we have the traveling salesman problem. More I will discuss, with examples when we come to that appropriate point. Supply chain management, we all know, is very important in today's world. Sending material to where it is required at the most opportune time. The network optimization problems are everywhere. We have those network, electrical network, the road network, the airline network. So there are different kinds of the social networks. So there are different kinds of networks. They're everywhere, and how to optimize them. Then project planning, we know project management is another very important problem. Facility location problems, where to locate our facility so as to obtain the best possible results. Now, these are the broad topics, that we are going to cover in this particular course. The first is the, topics that I shall be covering. These are linear programming, the formulation problems, the simplex algorithm, special cases in linear programming, minimization problems, duality concepts, complementary slackness, conditions, and also certain theorems with part as a part of duality concepts. Then the dual simplex method, and finally transportation and transshipment problems. This will be covered by me. I am from the Department of Industrial and Systems Engineering of IIT Kharagpur. My colleague, Professor Jitendra Kumar Jha, he from the same department at IIT Kharagpur, he will be covering the revised simplex method, sensitivity analysis, assignment problems, integer programming, pure binary and mixed, the knapsack problem, and the traveling salesman problem over 40 lectures. First 22 lectures will be given by me, and then Professor Jha would be giving the next 18 lectures. Now, coming to the linear programming, which is our first topic, as I have already said, it is about allocation of resources to a set of activities. The activities are basically maybe some kind of production, maybe how many vehicles to procure, maybe how many projects to run, maybe how many facilities to locate, and so on and so forth. The first thing that is a part of linear programming is the maximization or minimization of a linear objective function. So that objective function has to be a linear, and it has to be either maximized or minimized, subject to a number of linear constraints. You see, when we are talking about an optimization problem, we maximize or minimize an objective function, and we optimize the decision variables. There should be a set of decision variables, which are in this case the different activities. The constraints and the objective functions are linear. That means these constraints should be linear. The objective function should also be linear. And the activities considered in linear programming need to be non-negative for solving the problem. In reality, it is very difficult to really think of negative values of variables in a practical world. Theoretically, yes, there could be lots of problems in physics and other kind of sciences where you get negative numbers, but in the real world, it's very rare to find negative numbers. Having said that, you can also think of negative numbers definitely under some situations, but moment you try to solve a linear programming problem, it is extremely important that we must fulfill the non-negativity criteria. That means all the variables must be non-zero and bigger, they should be greater than equal to 0. The activities are represented by the decision variables. So that is the principal thing about linear programming. What really happens there in linear programming, you see this is a linear objective function, as I said, usually in the form of maximize z equal to sum over j equal to 1 to n cj xj. Here there are two things. We are talking about the maximization problem. In a maximization problem, if you see, Cj are the profit coefficients, Xj's are the decision variables. So if I have, say, 5 decision variables, so objective function is then maximize Z equal to C1 x1 plus C2 x2 plus C3 x3 plus C4 x4 plus C5 x5. And subject to the linear constraints. So what are some linear constraints? Linear constraints are here sum over j equal to 1 to n aij xj less than equal to bi for all I equal to 1 to m. Here, these BIs are the resources. Suppose there are 3 resources, then there will be 3 such constraints. In a standardized form, in a maximization problem, we are going to use the less than equal to sign. So these resource limit, that is that BI, B1, B2, B3 for 3 different resources should not be exceeded. And Aij is the coefficient, that means how much resource is required per unit of say xj. So if there are 4 different what you call activities or decision variables, then there will be 4 such terms, and sum of that, and Aij is how much resource is required for making 1 unit of xj. So that would together, if added for all the different activities, is the total resource requirement of that particular type, and that should be less than the resource available. So that is going to be a linear constraint. And thereafter, we also must have what is known as the non-negativity constraints, that is xj should be greater than equal to 0 for all j equal to 1 to n. So quick recap, what I just now said, that there should be an objective function, it should be linear, it should be subject to a set of linear constraints, and those linear constraints are additive in nature in the sense that if there are number of decision variables and each decision variable require certain amount of resource per unit, so total resource required of one type is Aij xj sum over j equal to 1 to n, and that should be less than equal to Bi, which is the total availability of the resources. So that is how the linear constraints are made for a maximization type of problem, where in the standard form all the constraints are about less than equal to, and we have the non-negativity constraint. So that is one type of problem we shall basically discuss, the linear programming, how to solve those problems, how to solve graphically, how to solve through the simplex algorithm, the special cases. So all these things I'll discuss a little bit in detail. The first thing about the simplex method. You see, the simplex method was developed by George Bernard Danzig, an American scientist. So the simplex algorithm is used for solving linear programming problems. What we do actually, we develop a set of simplex tables, and in this simplex table, a solution is represented in terms of basic and non-basic variables. These are important terms, the basic variables and the non-basic variables. The basic variables are basically those variables which are actually solved. You see, invariably we shall find for such kind of problems, there will be more number of variables than there are number of constraints. By adding more variables, we are making them as equality constraints, which is called an augmented problem. Now, when we try to solve the augmented problem and there are number of variables which are more than the number of equations, obviously we cannot solve. Suppose there are 10 variables and there are only 6 equations, we can only solve 6 of them. What we do with the other 4 variables? We put them to zeros. As we put them to zeros, obviously the other 6 can be solved. So those which we are putting to zeros, they are called non-basic variables, and those which we are solving and getting some solution, they are called the basic variables. Now the question is that why these solutions by putting the non-basic variables equals to 0 become candidates for optimal solutions. It's a very important question in the linear programming, that why by putting some non-basic variables to zeros and solving the equations in an augmented problem gives us some solutions which are candidates for the optimal solution. So this is a very, very basic thing about this linear programming, and we must understand that that is what we are going to look into, right? So that is what is one of the very important things, that the basic variables are solved and they will have some values. non-basic variables are put to zeros. As we spend more and more time, we shall make our understanding will be much clearer. Today, I'm just giving you an overall glimpse of the subject. Every simplex table should be in a canonical form. That is, the basic variables must form an unity matrix when taken in a particular order. What exactly it means? Say I just told that there are 10 variables, 4 of them are put to zeros. That means 6 are solved from 6 different equations in the augmented problem. Now the question is that these equations are to be written in such a way that one basic variable should be there in only one equation, right? So equation number 1 should have only, say, basic variable number 1. It will not be there in other 5 equations. Similarly, equation number 2, there will be only the one basic variable, that is basic variable number 2. Third equation, only the basic variable number 3. That is what we are calling a canonical form. So the simplex table should be in a canonical form. In a sense, you will realize later that the basic variables will form an unity matrix. Like 1 0 0 0 1 0 0 0 1, that type of matrix. And when that is achieved, we say the table is in canonical form, and this is extremely important for carrying out the simplex operation, the simplex method to apply and solve a linear programming problem. Another option, that is, how do I go from one simplex table to the next simplex table by a pivot operation. What this pivot operation does, it actually converts one canonical form to another canonical form. You see, if I have one basic solution represented by a particular simplex table, and that is not the optimal solution, we have to then exchange variables. One non-basic variable should be made a basic variable, and one basic variable should be made a non-basic variable. But the basic idea that the equations must be in a canonical form, that is, the next simplex table should also have that unity matrix, that is achieved by the pivot operation, is it not? So a pivot, a new simplex table is obtained in each iteration with a non-basic variable coming into the basis, with a basic variable leaving the basis. The process stops when an optimal solution is obtained. So that is in a nutshell is a simplex method. I know there will be many questions in your mind when you are hearing this because I have not even started the subject. I'm just trying to give you a glimpse of what is available here. Now there will be certain special cases in linear programming, which is going to be our next topic. Now, what are those different special cases? Usually there are 4 different special cases that are possible. The first one is called a degeneracy. Degenerate solutions arise because some values are zeros in the basis. So what happens that we said that there are basic variables and there are non-basic variables. The non-basic variables are put to zeros and the basic variables are solved. But after solving also some basic variables may get a zero value. When that happens, we actually have what is known as a degenerate solution. But why degeneracy is so important and why it is to be studied separately? You see, usually the degenerate solutions happen when more than one basic solutions overlap. And the simplex is moving from one basic solution to another basic solution. But imagine 3 solutions have overlapped and you are moving from one to the other. You are unnecessarily wasting time. Suppose you go from 1 to 2 and 2 to 3 and come back to 1. Basically, you have not progressed at all. You are simply cycling in a particular solution, a point which is known as a degenerate point. So we must identify those cases and try to see whether it's a permanent degeneracy or a temporary degeneracy. So this is one thing that has to be seen in a simplex table. The next thing that is also very important are called alternate optimal solutions. See, the alternate optimal solutions are possible when you see there is a solution space, and alternate optimal solutions could be available in a linear programming problem when the profit line, that means our objective function represented by a profit line, that can be parallel to one of the bounding constraints. When that happens, we are going to get multiple optimal solutions. It's not only two corner points, but also all the points joining those two corner points. So that also must be identified if you are using some simplex method. Third special case is an infeasible solution space. See, the constraints are such that there is no feasible solution space. If you are solving it graphically, yes, you can find them out. But if you are not solving graphically, if you are trying to solve it by simplex method, chances are that you may actually miss out. Why you should miss out? Because you are not able to see that whether there is a feasible solution space, yes or no. So under that situation, what is to be done? What is to be done is that we should see in our simplex procedure that there is some indication that the solution space is not feasible. And fourthly, there could be situations where the solution space is unbounded. So if the solution space is unbounded and it is a maximization problem, chances are that we are not able to solve the problem. Is it not? Because there is no solution. As we proceed, the values are increasing, and finally an infinite solution may be resulted. Right. Then special cases about these minimization problems is that minimization problems are unique in linear programming because they invariably involve greater than equal to constraints. You see, it is not that minimization problems only have equal to constraints. I have shown you before that greater than equal to constraints can also be there in maximization problem. But usually the minimization problems have what is known as greater than equal to constraints. Because look here, if you are minimizing something, ultimately there will be always an optimal solution that is 0, 0. That means do not produce anything. But that cannot be a solution. You have to produce something if there is a thing. Sometime, whether you make profit or loss, it is very important that you keep the business going, because the product itself is more important. Say, for example, a gold processing company. The question is that even if the company is under loss, gold processing is a very important activity and it must be carried out. Is it not? So say, for example, the railway service, the railway passenger service, it is loss making. We know it unless until it is air conditioned service. What happens? The passenger services, although it is loss making, but it's extremely important that it has to be provided for people at large. So if that is so important, and if you do cost minimization, then the solution obtained will be stop it. I mean, don't run any passenger trains. Alternately, if you say that, look here, we are interested in cost minimization, but a basic minimum service must be maintained. In other words, the total number of trains running and the passengers moved from one place to the other must be greater than equal to a set value. So what are we doing? We are minimizing a cost function subject to some greater than equal to constraints. So that is very normal and natural in minimization problems. You have what is known as the greater than equal to type of constraints. So when you try to solve such kind of problems, invariably you see if we want to have a canonical form, that is the basic variables forming an unity matrix, that is possible only when you add some artificial variables. These artificial variables particularly do not mean much. They are used only for solving the problem, and therefore they are associated with high penalties, very high penalties. In fact, they are called M, and the method is you sometimes called the big M method. Right. So now the question is, it is not, please also understand that artificial variables may be required in maximization problems also. It is prevalent in minimization problem, but nevertheless in maximization problems also it is quite okay. If you have greater than equal to constants, you have to use what is known as artificial variables, and we have to encounter the big M method. Fine. So that is about the minimization problems. Then after that, a very important thing, a very, very important concept, which is known as the duality concepts. You see, every linear programming problem is associated with another linear programming problem called its dual. The dual problem solves the same problem from another point of view. I'll give you an example. What is a dual problem? Let us say we have a profit maximization problem, and there is a problem that there are few resources, say 3 resources, and there are 2 products, and these 2 products are to be produced with the help of these 3 resources. So we are making let's say chairs and tables, and we have resources such as wood, the nails, and something, maybe the manpower or the people time of the people. So you see, these resources, the 3 different resources that we are going to use, and in a maximization problem, the 2 products, the chairs and tables that we are making, these chairs and tables, the problem will look like maximize some Cj, Zj, sum over, subject to the resource constraints, which are all less than equal to 0. And x1, x2, the chairs and tables, those unknown should be greater than equal to 0. So it's a maximization problem, and find out how many chairs and how many tables are to be produced so as to maximize the profit. Same problem, if you look at it from another point of view, let us assume that we are not going to make any chairs or tables, but we have those resources. Now, if we try to see that we want to give those resources in the market, right? We want to give those resources in the market. How much are we going to get from those resources? So you see, what you have to do under the situation to make the 2 problems equal, it must be the amount that we get by using those resources, by giving it to somebody else who may be producing chairs and tables. We must make at least that much profit that we are making now, is it not? From the wood, from the nails, and from the manpower point of view. Is it all right? So we must have at least that much profit. And to make the 2 problems equal, if the original problem is maximize profit, the other problem should be minimize cost. So this is what is known as a min-max kind of situation, that there is an alternate problem to the original problem. So if the original problem is primal, the other problem is going to be the dual. So there is a primal problem and there is a dual problem. The dual problem is the same problem looked at from another point of view. If one is maximization, other should be minimization. Sometimes solving the dual is easier than solving the primal. Hence, it gives another option of solving a difficult linear programming problem. Is it all right? So, and the dual of a dual is primal. So again, if you take the dual of the dual problem, you get back the original problem, that is the primal problem. You may be thinking that if every linear programming problem is associated with another problem, which we are calling the dual problem, what is it that why should you bother about it? What is so big about this duality that it is going to give us some additional insights. What are those insights, and why the duality is so important to us? You see, that lies in what is known as the complementary slackness. The optimal solution of a linear programming problem gives certain insights. If the optimal solution is put to the constraints of the problem, some of the constraints turns to equality. That is, the slacks have vanished for these constraints. You see, the original problem, if you recall, they are not equality, they are actually inequality problems. Now, in those inequality problems, if you simply put the optimal solutions, what are we going to get? What we are going to get, is that some of them may turn to equality. So when those turns to equality, we usually call the slacks are vanished. And we say that when slacks are vanished, the corresponding dual variables exist. On the other hand, if the primal slack does not vanish, then the corresponding dual variable values become zeros. All right. So what is this complementary slackness consideration? It actually helps in obtaining useful insights in many linear programming problems. A very good example is the transportation problem. You see, in transportation problem, what we can do, we can actually find out those, the complementary slackness, and from there, we can actually compute the solutions, the Cj minus Zj values very easily, right? So the complementary slackness conditions, the duality concepts, it has applications in many important areas. Another very important areas is the network. There is a network simplex method, which also is the duality concept helps in a big way, right? Beyond that, that also gives us another very important kind of simplex method, which is known as the dual simplex method. This is going to be our next topic, the dual simplex method. I told you a few minutes back that when we have the greater than equal to kind of, constraints, we require artificial variables to solve linear programming problems. Having greater than equal to constraints. Such problem can be greatly simplified by using dual simplex method. What dual simplex method does, it will be understood when we actually do it. It actually solves the problem from another angle. The normal simplex method, it actually tries, searches for optimality while maintaining feasibility. But the dual simplex method is the opposite. What it does, it actually searches for feasibility while retaining optimality. So the feasibility optimality is just the opposite in case of dual simplex method. The process stops once the feasibility of the solution is achieved. I know there are lots of terms we are using, which is maybe for the first class, it is appearing to be a little complex. But essentially, it is very important that we get the broad idea what this dual simplex method does. You see what happens in simplex tables, the values of the variables should not be negative. But the dual simplex method starts with some of the basic variable values at negative, right? So which is an infeasible point. So starting from that infeasible point, it actually goes through the operation and tries to find out how exactly you can actually solve those problems in those matters. One thing before I proceed further to the further topics, you see, you may be thinking that if software is available, what is the need for the conceptual thing? Most of the time, you see the challenges that lies in simplex or linear programming problems is not solving it. It actually about formulating the problem and try to get a quick interpretation, trying to get a quick idea about how these particular linear programming problem solutions are going to be. So in real world, when there are hundreds of variables and so many constraints, maybe hundreds of constraints also, you see any insight that actually simplifies the problem helps in a tremendous manner. For example, if you look at a paint company, you see most of the paint companies, they try to produce different kinds of paints. So when they produce different kinds of paints, and all these different kinds of paints, they require several production steps. And in different production steps, different kinds of resources, machines, manpower, raw material, they are all required. A solution could be obtained if you know the amount of resources which is available for a particular month. In the beginning of the month, you can put all those resources in the computer, their values, and you know how much is the targets. You can run a linear programming problem and you can get an initial quick solution. And that initial quick solution can help in understanding the problem situation in a very big way. All right, what you may require to run the program once again in the next month. So when you are writing such a program, or when you are optimizing such a program, the conceptual knowledge is also going to help you in a very big way. Another area of application is the supply chain management area. See, today in the supply chain managements are becoming bigger and bigger, starting from local supply chains of a company. Now people are talking about conglomerates. People are talking about very big supply chains, which not only includes the parent company, but its suppliers, the suppliers of suppliers, and vendors, the clients, your clients and clients of clients. So slowly the supply chains are becoming bigger and bigger. So with bigger supply chains, if you try to solve the problem size will be big. And for such a big problem, if you want to solve, the conceptual understanding, ability to formulate is going to be very important in real world. Having said that, now let us move to our next important problem, that is known as the transportation problems. Transportation problems attempt to find out how to send materials from a set of sources to a set of destinations with the least possible cost of transportation within the source availabilities while fulfilling the destination demands. So there are several sources and there are several destinations. So from the source to the destination, there are different paths. Let's say as a special case, let us assume all sources are connected to all destinations. But the cost of transportation is different. Source 1 to destination 1 and source 1 to destination 2 or destination 3, the costs are different. The unit cost of transportation, that means transporting one unit from source 1 to destination 1 or source I to destination I, is different. So when it is different, obviously the question comes that if we have the source availabilities and the destination demands, how much should be sent from which source to which destination? That is, in a nutshell, is a transportation problem. Now, the solving the unconstrained one with only the demand and availability constraints is difficult. So we make an assumption, an overwhelming assumption to solve this problem, that total availabilities are equal to the total demand. So that is the assumption we make. So you may be thinking that suppose they are not equal, then what should we do? We can add then either a dummy source or a dummy destination. So by adding dummy sources or dummy destinations, you can make the total availabilities equal to the total demand. What is achieved by making this assumption? What we achieve is that moment you make this thing that total availabilities are equal to the total demand, you can see very easily that all the constraints are now become equality constraints. That is the advantage. So now we are solving a problem with a number of equality constraints, and because the constraints are equality, solving will be easier. Is not that is what is a transportation algorithm. It is definitely a linear programming problem, a special case of linear programming problem. And what is special here? All the coefficients are equal to 1. Since the coefficient matrix are all 1, apart from the basic variables, obviously they are in unity matrix, so 1, 0, 0, etc. For all the other terms are 1. Because this is so, solving is easier, and there is no need to really solve the simplex problem in the usual way, right? We can have specialized algorithm for solving the transportation problems. So usually no restrictions are allowed for a source to deliver to any of the destinations or demand points, and no intermediate nodes are allowed. So that is what is usually done in transportation problem. A transshipment problem, on the other hand, is also a transportation problem with additional relaxation. What is that additional relaxation? The material can be transported from source to destination, destination to source, source to source, or even destination to destination. So these allows additional opportunities to reduce cost. So you see, you may be thinking that source 1 to destination 1 and source 1 to destination 2, instead of sending them separately, why not you send the entire material to destination 1, and whatever destination 2 wants, let them take it from destination 1 itself. All right. Another option could be there could as well be some intermediate nodes. That is, all the material may be sent to some hub, maybe an intermediate node, and from that hub, the material may be going to different destinations. So all those different options can also be considered in a transshipment problem. So it is a special case of transportation algorithm, but since additional relaxations are available, the algorithm will be slightly different and more options are obtained. That is what we do in what is known as the transshipment problems. Now I'll come to the other side of the thing, that the kind of lectures which will be given by my colleague Professor J.K. Jha. Some of the things, that is, one thing is the revised simplex method. You see, what is the revised simplex method? There is a matrix which is known as the B inverse matrix. It's a very important matrix. When we say B, it is the capital B. This capital B is known as the basis matrix, and inverse of that matrix is the B inverse matrix. What happens? The B inverse matrix is formed by the basic variables of the first table in a given simplex table. So suppose you are doing simplex operation, and in the first table you could find out the basis matrix. Which are the basic variables? These basic variables of the first table, that in the second matrix that it should be forming, that is known as the B inverse matrix. Now looking separately, looking differently, the B matrix is therefore which is known as the basis matrix. This basis matrix will be actually formed by the variables that are in the basis of the given simplex table, not the first table, in the first table, right? So suppose I know what are the basic variables, what are the basic variables of a given simplex table. If we can find out, suppose there is a first table and there are second table, we know the basic variables of the second table because we know that which variable is leaving the basis and which variable is entering the basis. So from that basis matrix formed in the first table, we can invert the matrix and we can get the B inverse matrix. If we follow the usual simplex procedure, obviously the simplex procedure itself will invert the matrix. But in revised simplex method, we have to find out the variables of the basis, then form the basis matrix and actually invert it. now there is a rule that says the multiplying B inverse matrix with any column of the first table will give us the corresponding column of the given simplex table. That means that if we know the B inverse matrix and if we multiply the first column of the first table, I will get the first column of the next simplex table, from that operation. So similarly, I can get the second column. Similarly, I can get the third column. And similarly, I can get all the columns. That means if B inverse matrix is known, using that B inverse matrix, I can find out all the columns of the second table. So that way, we can make a second table from the first table, but with the help of the B inverse matrix, right? And proceeding in this manner is called the revised simplex method. All right, this is a very powerful technique, and using this revised simplex method, we can also solve the simplex problem in a particular way. Now, that also gives the idea the sensitivity analysis. Now, after solving a simplex problem, it is sometimes important to find the sensitivity of the changes related to the objective function, the constraints of the resource quantities on the final solution that is carried out by the sensitivity analysis. Say, for example, we have a problem. Now, after solving the problem, suddenly it comes to our notice that the some resource value could be available in additional quantity. So originally the resource was available in certain quantity and it has become a bottleneck resource which has affected the optimal solution. Now it was asked that suppose that resource is available in more quantity, will it going to change our the solution, the final solution? The answer to it is yes, it is possible. That is what, that is again the B inverse matrix is handy there. Use the B inverse matrix with the new value and find the new solution quickly. From the first table, we can go directly to the final table and we can find the new solution. It is not that all kinds of sensitivities can be found out by B inverse matrix. That is not true. There are other methods of sensitivity. Those will be discussed in detail when the sensitivity analysis is going to be discussed. The assignment problem is again another special case of linear programming problem. In fact, to be put more accurately, the assignment problem are special cases of transportation problems, right? So transportation problems are special cases of linear programming problem, and assignment problems are special cases of transportation problems. What are they? How they are special cases of transportation problems? When all availabilities and all demands are equal to 1, right? Invariably that gives us a square matrix. Now looking to it, assignment problems are uniquely assigned machines to jobs, people to jobs, contracts to contractors, or swimming lanes to swimmers while minimizing a cost function. You see, suppose there are 3 jobs which are to be allotted to 3 people. If there are 3 people, they are good at 3 different jobs. First one in first job, second one in second job, third one in third job. It's very easy to assign people. Whoever is good in which job, simply assign them there. But look here, suppose in the job 1, all 3 people are okay, right? In the job 2, first 2 people are okay. And in job 3, last 2 people are okay. Then who should be assigned where? So you see, the situations could be very complex when it is not clearly identifiable who is doing who is best in which job, right? So when that doesn't happen, it could be more complex with more number of people, more number of jobs. Suppose you are assigning 10 jobs to 10 people. Now there are 5 people who are good in first job, 2 are excellent in fact, but another one, he is not so good in job 1, but he is not good in any one. In fact, job 1 is a job where he is somewhat okay. So those kind of situations are going to happen. And we might get a much better solution if we actually solve it by assignment problem algorithm. All right. And there are very simple Hungarian methods are available to solve assignment problems, which are much simpler than the simplex algorithm. And therefore, much bigger problems can be solved, easily with the help of the assignment algorithms. Integer programming. See, another very important concept of integer programming. See, there is an assumption of linear programming that is called the divisibility assumption. The divisibility assumption essentially says that the values of the variables can, be divisible to any extent. That means a solution of 7.2 is quite acceptable. Even 8.15 is quite acceptable. But 8.15 people, 7.2 jobs done, these are not something that we are ready to accept easily. So what really happens under such situations, it is important, when the integer solutions are much more important than fractional solutions, we have to solve the problem differently. There could be binary variables also. Consideration of binary variables allow modeling of many different logical constraints. Many different real life situations can be modeled as integer programs. There are efficient algorithms such as branch and bound algorithms to solve integer programming problem. So we can have pure integer programming problems where integer solutions could be any value and not just 0 and 1. If they are 0 and 1, they are called binary, or there could be mixed integer programming problems. In a mixed integer programming problem, some of the variable values are integers, others are not, right? Integers are binary, others are not. So there could be pure integer programming problems, there could be binary integer programming problems, and there could be MIP or mixed integer programming problems, right? All these different problems can be solved by different techniques, and one such very important techniques is a branch and bound algorithm. So this branch and bound algorithm will be discussed while discussing integer programming. Knapsack problem. This is another very important problem. The knapsack problem is, the example is given here. Knapsack is to be stacked with items. Each item is having a weight and a value. So look, this is our knapsack with a total weight restriction, and each item has a weight and a value. So what we need to do, we need to find out how many of each type of items are to be stacked into the knapsack so as to maximize the total value within the total weight restrictions. Is it not? Something like you have your knapsack and you have all these items. You can only carry certain amount of weight. So which of these items will you take so that within your knapsack you get maximum amount of value, right? So that's a very important thing about knapsack problems. The knapsack problems can be in many situations, in wagon loading, in a railway wagons when they are loaded in the sidings with coal or any other such raw material, how to really load them in the best possible way so that maximum value can be carried. And similarly, there could be many different solutions or different formulations can actually be thought of, right? So this is one very important problem that will be discussed. And finally, the traveling salesman problem. Traveling salesman problem is finding minimum cost, distance or time tour that ends in the starting city for a salesman visiting n cities, where each city is visited exactly once. So this is a traveling salesman problem. Starting from city 1, you have to go to all the cities exactly once by minimum possible cost or distance. So maybe the path should be 1 to 2, 2 to 5, 5 to 4, 4 to 3, and 3 to 1, right? Look here, it is a feasible tour. But suppose you go 1 to 2 to 3 and to 1, or 5 to 4 and back from 4 to 5, then you don't get a tour. So that's not a traveling salesman problem solution. See, many real life problems can be solved with the help of traveling salesman problem. There are lots of very, very interesting examples. You know, suppose in the time of miniaturization, how do you locate your ICs within a small, holder, and how exactly you should put their electrical connections, assume order is not important, so that they can be held in the smallest size block. It can be represented by a traveling salesman problem, right? So there could be many different examples where the traveling salesman problem is a very important consideration and can actually be solved. Is it all right? So that is about the course that we are going to give over 40 lectures. Here are some very important reference books. I have given 4 books here. Not only that, these 4 books are only there. There are many, many other books which are also very important. But anyhow, I have listed 4. Introductions to Operations Research by Frederick S. Hillier and Gerald J. Lieberman et al. There are other authors also. Operations Research and Introduction by Hamdi A. Taha is another very good book. Principles of Operations Research with Applications to Managerial Decisions by Harvey Wagner. And finally, Operations Research Principles and Practice by Rabindran, Phillips, and Solberg. Is all right? Now, I shall be following the conventions of these Rabindran, Phillips, and Solberg book. Mostly the simplex convention I shall be taking from Rabindran's book, which is also very good. But if you really look for concepts, the Hillier and Lieberman, along with other authors, that book is very good from a conceptual point of view. Is it all right? So there are many other books. It is not which book you study, that's not very important. What is important that you understand the concepts and you can solve problems, or you can formulate problem. That is the quality that is required from this particular subject. Here are the lecture-wise details. So I shall be covering 22 lectures. So these are the lecture-wise details from lecture 1 to lecture 11 out here. This is the introduction to operations research. The next one will be linear programming basic concepts. Then the simplex method, then the special cases in linear programming, minimization problems, then duality concepts, dual simplex method, transportation problems, and transshipment problems. Then Professor Jha will be taking over and he will give lectures on revised simplex, then sensitivity analysis, different methods, the assignment problems, and integer programming problems in great detail with formulation, pure integer programming, knapsack, binary integer, mixed integer, knapsack problem, traveling salesman problem. Is it all right? So this is about this particular course, and I hope that it will be a good journey for all of us to go through these lectures. So thank you very much.